Where does that start? No, page 20, hematologic tests. And so I'm using this picture because the vial of blood is nice to point at. But let's go ahead and do it in order just so it's easy for you guys to take notes. So total white blood cell count, that's exactly what it sounds like. You can basically do a differential or a total white blood cell count. On your sheet it's total, but you may hear it referred to as differential, and that's when you're going through and actually counting within a specific amount of blood, and this is on a microscope. You're counting how many neutrophils there are, how many eosinophils there are, how many basophils there are, how many lymphocytes, how many monocytes. And the importance of that is that by elevating certain elevations in certain white blood cells will tell you potentially what's going on in that individual's body. So that's a real basic microscopic thing to do, and that's referred to as a total white blood cell count. The three things listed below it are three very general ways to describe the results of a total white blood cell count. So leukocytosis is too many white blood cells. Leukopenia is too few white blood cells. And leukemia is a specific type of leukocytosis where the underlying cause is some type of blood cancer, but its result is too many white blood cells. So it's sort of, leukemia is a subtype of leukocytosis, is the best way to think about it. And so as you notice and probably know already, leuko, that prefix is referring to white blood cells. So you break down these words, they can really help you understand what's going on. So that's the deal with white blood cells, but where you're actually going to see them, today you're going to look under a microscope and they're not going to look white at all. They're going to have a lot of different features that are going to allow you to identify each one. But when you actually draw blood out, blood starts as a suspension, meaning that the red blood cells are actually not dissolved in your blood. They're simply suspended in it. So they don't actually interact directly with the water. They're surrounded by it. It's like when you jump in a pool, you're not dissolved in the pool. That would be a horrible situation. That would be like a Breaking Bad situation. And now, like the second episode, they dissolve someone. That's totally, that's actually dissolving it. What's that?
That was a bathtub then.
But he dissolved too.
Yeah.
He was in the bathtub. Anyway. So we like when we get in a pool, we're not actually dissolved in the pool, we're just in it. Well, that's our red blood cells too. And the result of that is that if you actually take red blood and you sit it out, like this, it's going to separate. Things that are dissolved don't separate. You take salt water and just sit it there, the salt doesn't go to the bottom unless there's too much of it. And so that's why we refer to this as a suspension. And it's important to break apart the different components because then you can see erythrocytes, the little buffy coat, that's where our leukocytes are, that's where they get their white name, is because they are actually white when you get enough of them together, and there's not a whole lot else mixed in there. So they'll actually appear white. And then the yellow here, which hopefully isn't actually this yellow in you, hopefully it's much closer to looking like water, that's just your plasma. And so total red blood cell count, you could also count up the red blood cells, obviously, although it's a lot harder because there are way more of them than our white blood cells. A total red blood cell count is not a particularly useful thing. We're going to talk about hematocrit in a second and talk about how that's actually much more useful to measure. But if you try to quantify the red blood cells in your body, you could have a normal result, which is listed further down on your list there. Or you can have an abnormal result where you can have polycythemia, which is too many red blood cells, and anemia, which is too few. And so those are, again, just two terms, too many and too few of the red blood cells this time, but instead of the white blood cells like we were talking about before. Now as we get into hematocrit, this is a much more useful way to measure things. However, I do want to point out that packed cell volume is something that you may hear used, and your textbook really likes to use this term. It's a way less useful term, and let me tell you why. So hematocrit, I want you to put in parentheses, I want you to think about this, and many of you, if you've dealt with this before, already think of it this way. Hematocrit is a percentage. It is not a volume. It is not a distance. It's a percentage. So it is a number, for instance, like 42%, which would be the normal female value for the percent of your blood that comes out of your arm that's actually made of red blood cells. Whereas packed cell volume is the volume that your red blood cells take up. You could take both of those measurements from this vial here, but the reason packed cell volume is not as useful is because if I say, hey, you got 5 milliliters packed cell volume, it doesn't actually tell you the proportion of their blood that is red blood cells. And that's the important one. And the only thing that tells you the percentage is the hematocrit. So clinically, that's normally what you're going to use. So you can see the two numbers, normal female and normal male, about 42% and about 47% for male values. You're going to see these numbers significantly lower in acute settings because whether or not someone's had a procedure done to them or has some symptoms that cause anemia or something like that, you may see these numbers lower. I've seen somebody with 27% as their hematocrit. I'm sure it gets even lower than that. But normally you're hoping to be definitely above that 40% mark, but it does vary. It varies for both males and females, and it varies slightly more for females. So hematocrit, percentage, packed cell volume, a volume. Percentages are just so much more useful because when I tell you you have a red blood cell or you have a hematocrit of 45%, that's the end of the story. You don't need to say how big someone is. You don't need to say what sex they are. You don't need to say anything else. You just take their blood out and you take a look at what percentage of the total volume is taken up by red blood cells. And we ignore the white blood cells as a component of this concept because they're less than 1% in most people, and therefore they don't have a huge effect. You're basically saying in most people, 45% red blood cells, 55% plasma. That's kind of our normal thing. And we're really high on the scale compared to other animals. We have a really hyped up cardiovascular system, and so we try to carry a lot of oxygen. And in order to do that, we need a lot of red blood cells. Now you can run into an issue with your hematocrit though, not just being too low, like I mentioned before, but it can also be too high. So again, that's the term polycythemia. So that would be referring to too many red blood cells. But this comes up for two different reasons. One is blood doping. So in a couple different ways, either through EPO or from actually freezing your own red blood cells and injecting them into your body before an athletic event, you can actually increase your hematocrit and cause polycythemia. And the advantage to this should be sort of obvious. You're going to carry more oxygen. So for endurance events, this is important. You don't see sprinters doing this because they're not using the oxygen in their blood much. But for cyclists have become very famous for it, but in a lot of other endurance sports, having a larger hematocrit or causing polycythemia will actually make you perform better. The problem is, at a certain point, your blood, right now our blood is somewhere between syrup and water in terms of its consistency. It does not flow. You guys have seen blood run down things. It doesn't run as fast as water, but it runs faster than syrup. And so we're right in the middle. The goal, though, for us is to not get it too much like syrup. And blood doping can do that. Once you get above about 55% red blood cells or 55% hematocrit, then your blood, the viscosity of your blood is much more similar to syrup, and you can actually cause cardiovascular failure. So one is blood doping. That's the sexy one. I think it's in the news. The other one's dehydration. So dehydration is listed on your notes because it's actually the most common way that you're going to have increased hematocrit. It's not going to be because you intrinsically produce more red blood cells. It's because if you imagine this vial, and let's say I pull out half of the plasma and I leave it all the same. If I were to pull out half of this plasma, now the fraction or the percentage of your blood that's made of red blood cells would actually be closer to 75%. And so you don't actually have to change the number of red blood cells to change your hematocrit. You can simply subtract plasma. And the easiest way to do that is by not drinking water. And the second easiest would be go outside and exercise and evaporate all of your water away. And so in older individuals, when their esophagus stops working, so my grandpa's in this state right now, he's like 97 and a half, almost 98. And so he just struggles to control his esophagus, right? So he can't actually drink water. They're afraid he'll pour it into his lungs because he can't control that interface between the trachea and the esophagus very well. So they mix in a thickener, and it's horrible. It tastes terrible. It doesn't make you want to drink water. It makes water unrefreshing. So the problem is this, he just stops drinking. And so he has a replaced heart valve. His heart's okay for a 90-year-old. It's on maybe the little bit lower side of okay. But if he sits for 3 days and doesn't drink any water like he did a couple weeks ago, he's not very active, so he's not evaporating much water away, but he's not taking any in. His hematocrit is creeping up, his blood's becoming more and more like syrup, and he'll just have a heart attack there if no one notices that this happens. But that's why you monitor fluids, right? So they knew it was happening, but that's the most common clinically relevant way you're going to get an increase in hematocrit. And so it's just a different way to think about it. Just subtract plasma, and that's your big worry. And that's what'll kill you when you get dehydrated, like out in the desert and stuff like that, too. All right, hemoglobin concentration. So hemoglobin concentration, you can judge this based on the color of the blood, actually. And so they have really specific light sensors now that are doing this. There's a lot of research that goes into accurately measuring things in the blood. The color of red is the easiest thing to measure. It's very easy to measure like the wavelength of light coming off of something, but what they're starting to do is try to measure blood glucose through the skin, like through a camera, basically in the bottom of the iWatch. Apple bought a company 3 years ago that does that because they want to be able to monitor blood glucose continuously without actually removing blood. Really cool thing. But again, everything that's ever tried to measure through the skin is all based on color changes, really subtle ones. Easy to do with oxygen, a little harder to do with glucose. But hemoglobin concentration is another one that you can measure through color change. And so hemoglobin concentration, let me draw out the big difference because it seems like maybe, okay, why do we have so many different ways we can measure the blood? Well, hematocrit, what we were just talking about up to this point, was all about changing the numbers of cells. We haven't talked about changing the properties of the cell itself. So with hematocrit, it's going to be blue blood. With hematocrit, we were like, if this is person number 1 here, and this is person number 2, hematocrit is just counting cells in a certain volume of fluid, right? Obviously, there'd be way more, but I don't want to draw more cells. So this person would have a higher hematocrit than this one because there's more red blood cells. But hematocrit doesn't tell you anything about what's inside of the cells, how much hemoglobin's in each cell. So for instance, this person may have more red blood cells, but if my dots represent hemoglobin, this person could still have a higher hemoglobin concentration because the cells that they have are packed much more closely together with hemoglobin. So does that make sense? That difference. One is measuring cells. That's the only thing we talked about up to this point. The other one is actually taking into account how much hemoglobin is there. And so when you look at oxygen carrying capacity, it's very easy to think of just the red blood cells. But you do have to take into account what the hemoglobin concentration actually is inside of each cell. All right, let me make sure I hit everything on that page. All right, so our last two, actually,